In this problem, you're given a frequency of 7.5 times 10 to the 14th hertz, and you're asked to calculate both the wavelength and the energy associated with this light wave. Well, if we're going to calculate, first off, looking at wavelength, which we remember shown by the sign lambda, the symbol lambda, and energy is going to equal, we have two options, h, which is Planck's constant, times frequency, or we could use the fact that energy equals Planck's constant times the speed of light divided by lambda, our wavelength. In the second equation, we rearranged our speed of light equation. C equals lambda times frequency. If we solve for frequency, we would have speed of light divided by lambda. If you notice, all I'm doing is substituting this equivalent into this equation. So where you have frequency here, I substituted what frequency equals into the energy equation. You can use either to solve for this problem. So let's start. We are given a frequency, and we're first asked to solve for a wavelength. So let's use our speed of light equation. We're solving for a wavelength, so wavelength equals speed of light divided by frequency. We use the 3.0 times 10 to the 8 meters per second. Divide that by our frequency. Our given frequency in this case is 7.5 times 10 to the 14th hertz. Remember, hertz is equal to cycles per second, so technically 7.5 times 10 to the 14th waves per second. And we can solve. And we're going to solve and get an answer in meters. So 4.0 times 10 to the 7 meters. Negative 7 meters. But remember, we now have an answer in meters. And the question, if it asks for nanometers, we'd have to convert meters into nanometers. Using the information that 1 nanometer equals 1 times 10 to the negative 9 meters, we can take the 4.0 times 10 to the negative 7 meters. 1 nanometer equals 1 times 10 to the negative 9 meters, and that's going to give us a wavelength of 400 nanometers. We want to have two sig figs because our initial value had two sig figs. So 400 and two significant figures would be 4.0 times 10 to the second nanometers. You have two options to complete the second half. You can take this given wavelength and the given frequency, plug them into, this given wavelength and the speed of light Planck's constant and plug them into this equation. Or you can take the energy equation and just take Planck's constant, which is a value that's on your manila sheet, the given value, it's not going to change, and multiply it by the frequency that you're given. So let's do Planck's constant times frequency. Planck's constant is stated to be 6.63 times 10 to the negative 34 joule seconds, meaning joule and seconds, both in the numerator. Multiply that by your frequency, the 7.5 times 10 to the 14th cycles per second. You're going to see that seconds will end up canceling. We're left with just joules, which makes sense because we are solving for energy. And in this case, our value will be 5.0 times 10 to the negative 19 joules. So we have our given amount of energy, and we have our associated wavelength.